Okay, so I'm gonna go a little fast. Stop me if you need to. So basically, at any typical moment, the chain will look like this, and then we'll have gotten some of it's being moved. So here's our original 10-foot length. Okay, and so if we start from, say, here, and we call that x, so x would be the distance so far that we've lifted the bottom length of the chain. Okay, that's the distance so far that we've lifted the bottom length of the chain. Then what we want to do is we want to calculate, so the work required right now to move it a little bit. Right, so for x, so if we, for any given x distance from the bottom that we've now lifted, we want to get the work for the next little amount, right? So we want, again, so a little amount of work. So typical little amount of work would be like delta W, okay? Okay, and that's going to be, we know that's going to be force times distance, force times a little bit of distance, right? So what would a little bit of distance be? Delta x, okay? So now, what's the force? Well, the force is the current weight of chain that we have to lift. How much chain do we have to lift right now? Right? Because this force is going to be the weight of the chain that we're currently holding up or lifting up. And so how much would that be?
12.5.
What is it?
12.5. Half the chain weight.
But x could be any amount, right? So x could be down here, it could be here, it could be here, it could be here. What's that? No, this is a variable amount of force, right? The amount at x. So if we lifted the bottom of the chain x, the amount of weight is going to depend on x, right? So we were saying actual values. So the more that we move, the more that we lift x, what's going to happen to the weight? It's going to be heavier, it's going to increase. So it can't be a constant number. It's going to be a function of x, this amount of force, the amount of weight. So how much weight are we currently lifting up if we've taken the bottom length up a distance of x right now?
2.5.
Okay, so first of all, it's not going to be 9.8 because we're in pounds and feet. So we said the whole chain weighs 25 pounds. So we're going to need to get how much 1 foot weighs, right? So this chain weighs 2.5 pounds for every foot. So now if we know how many feet is this right here?
Is it 2.5 delta x?
No, delta x is how far we're going to move this little amount. We're asking how much weight are we lifting or carrying right now, okay? So that would be for this much chain. So how much chain right now how many feet of chain are we holding up or lifting up a little bit?
2.5x.
No? What length of chain?
12.5.
10 minus x.
Okay, so we're asking what this distance is. And then we're going to multiply that by 2.5 to get how much that weighs. How much?
10 minus x.
No, because it's x over 2. It's x over 2, right? If we've lifted this far, up a distance of x, then that must be half of x. It used to be down here, and now it's up here, so it has to be x over 2, right? It's not crazy. It's great. It's crazy that we're all seeing different things. But do you see that that's x over 2? The length of chain that we've lifted so far? Do you see that? And so now how much does that amount of chain weigh, or what's the force?
2.5x
2.5 pounds per foot times the number of feet, x over 2. So that's the force. The force per foot times the number of feet that we're currently holding up. And then we're going to move that a little tiny distance. And then we're going to do that from what to what? 0 to 5.
0 to 10.
0 to 10. We're talking about x is the distance that we've lifted the bottom link.
Oh.
So it's going to start at 0 and go all the way up to 10. So this is one way to do this. And that, if you do that, you get 62.5 joules. No, foot-pounds. Okay, any questions on that? Does that make sense? That's one way to think about it. So here's a totally different way to think about it. What we can think about is, instead of how much chain we're currently holding and moving that up just a little bit and then adding up all that work, we can think about it this way. Look at, so again, we'll do x, say, goes up this way like this. And we're going to look at, say, this little link of chain right here. And ask, how much work does it take for that little amount, how far we're going to have to move that little amount of chain? How much work will it take? So calculate delta work for that little bit of chain.
Which could be any length, right?
Could be any length.
Length.
Any link the whole way up. Which links now are we looking at?
0 to 5.
Yeah, so all these links up here don't move. So we're just going to look at all the links, or all the little bits of chain in the bottom, and they're all going to end up somewhere, right? So this one's going to end up here. This one's going to end up here. The bottom one's going to end up where? The top. So we're going to look at a little bit of chain in the bottom half, and then calculate the work for that little bit of chain to go to its final place. All right, so delta W equals force times distance. So the force is now the weight of that little amount of chain. So how much weight is the weight of a little bit of the amount of chain, say, where we've shown right here? Well, how much does that little bit of chain weigh?
2.5x.
2.5x? That little bit of chain right there? What do you guys think?
Not x.
What should it be? 2.5 times delta x. So here now the delta x is part of the weight, not the distance that we're moving, you see? So this 2.5 delta x is the weight of a little bit of the chain, right? You see it? Pounds per foot times number of feet gives you, that's your F, times the distance. So what distance does each one of these go? Do they all go the same distance? No. They all go a different distance according to x. How can we figure out? According to, if we take the little part of the chain, x distance from the bottom, how far does that little bit of the chain go? How can we figure it out?
2x. Isn't it symmetric about 5?
Okay. Yeah, like the ones at the bottom go the furthest, and then as x goes, as you increase x, you go shorter and shorter distance up, right?
So it's twice the distance it is from the center.
What's that?
Twice the distance it is.
Okay, that would be one way to think of it. Yeah,
So
twice.
4 times 5 minus x.
Yeah. Yeah, so that's good. Twice the distance that it is from the center. And so let's practice though setting up. Let's practice setting up a linear function. So this is the idea of linear function, that depending on what x is going to be your distance, and that's going to be a linear function. So when x is 0, what is the distance that it's going to travel? That little link that's at x equals 0.
5.
He wants 5. Agree with that? Where's x equals 0 down here? Does that go a distance of 5?
Because 0
Goes
goes 10.
10,
Ah,
right?
Yes.
What about at the middle? When x is 5, how far does that piece go?
0.
Goes 0, right? And in between, it's going to be linear. So for instance, if you had 2.5, how far will that go?
7.5.
If you're at 2.5, it's going to go 7.5? It's going to go 5, right?
All 5, yeah.
So again, what we've got here is a linear relationship. D as a function of x. And so let's think of it this way, and then we'll check it with what you said, what half the distance from the center, right? So what we get when we do this linear relationship should be the same as like twice the distance that you are from the center, which is what you originally said. Okay, so we can get our rate of change here. It's going to be delta d over delta x, which is, we'll just use these first two. Delta d over delta x is going to be negative 10 over 5, or negative 2. And then when x is 0, d is 10. Therefore, d equals what? Negative 2x plus 10. So that's the distance. If the little bit of chain x from the bottom, the distance it goes is negative 2x plus 10. So what would twice the distance from halfway be? Twice the distance from halfway would be 5 minus x times 2. So this is what Kesman said originally, right? So the distance from x to the middle will be 5 minus x, and then it would go twice that far. Is that the same as this? Yeah, right. 10 minus 2x. But I just wanted to practice setting up linear function, because you might not be able to always just. That was really good, but you might not be able to always just do that. And so we need that skill of, let's look at some ordered pairs and come up with a linear function. Okay, now we're going to integrate from what to what? Oh, question, yeah.
Could you say your axis so that x would equal 0 at the halfway point of the chain,
Uh-huh.
and just have 2x for your equation, which would be 2x, right?
You want x to be what?
If x was at 0 at the midpoint of the chain.
And you're going down this way?
Yeah.
Yeah, that'd be a different frame of reference.
Okay.
So then how far? Right, then it would go 2x. That's right. Okay, and then we're going to integrate this from what to what? So now this integral is going to be from 0 to 10 again. So now we have 2.5 times negative 2x plus 10 dx from what to what? X going from 0 to 10 again? 0 to 5. The last one that we're going to move is right before 5. Okay, and you'll get the exact same number, 62.5 foot-pounds. Totally different way to think of it, though. In this way, we're thinking about lifting all the current chain that we're holding, right? A little bit. So the distance is a little bit for all that weight of chain that we have, right? The distance is a little bit for all the weight of chain that we're holding. This one is the weight of a little bit of chain, and what distance are we moving that little bit of chain? But both are force times distance, and both give you the same amount of work, because it's the same problem, both ways. Okay, did you follow all that? So this is the kind of skill level you need to be good at these physics problems, is be able to see and approach it in different ways. So questions? Anybody have a question? So let's apply this to emptying a tank. All right, so emptying a tank means you gotta lift a bunch of fluid or water or something out of the tank up in the air and get it out over the sides. That requires work, right? That requires work to lift the fluid up, pump it out. So, last chance for questions on this problem. Yeah.
I don't know why I saw the problem like this, but originally I read it as if like you were to pick the chain up like this and just bring it up to the top instead of going like this. In that case, it would be just X times over 2, right? Because you're bringing the weight of the whole chain, not half of it.
So it's,
Almost just like you lifted the whole chain all the way up to the top, all the way. Instead of grabbing it and like bringing it up, so you're only actually.
yeah, so that wouldn't require an integral because your force would be constant. Your weight would be the same for the whole distance. So you just do the whole weight of the chain for the whole height that you lift it. So you wouldn't need an integral. You mean not when you did it here today? I mean, did you understand it? You understood it? Okay. Okay. So let's look at emptying. Removing fluid from a tank. Okay, so removing the work for removing fluid from a tank. So to get the force to lift something, whether it's fluid or anything, what is the force required to lift something? And what is that called? What's that? What is that in general? The weight. All right. So the force required to lift something is its weight. Weight is a type of force, and if we're lifting something against gravity, then the work that we're using is going to be force times distance, and that force is going to be the weight force. Okay, the weight force. So with fluids, you're often given, it'll be like water or something, and you'll know its density, and so from its density we have to get its weight. Okay, so here's an example. The density of water is 1,000 kilograms per meter cubed, and that's a mass density because that's kilograms, right? And remember, in the English system, we usually bypass mass. We don't normally talk about mass in the English system, so we would be right to weight density or force density, and that would be 62.5 pounds per foot cubed for this water. So how would we get the weight density in the metric system? So if we wanted weight density in the metric system, what would it be? Right, so if the mass is 1,000, then the corresponding force would be m times 9.8 g. So for weight density in the metric system, it would be what? 9.8 times this, or 9,800 watt per meter cube. What's weight in metric? What's a metric weight measurement? Newtons.
That's called weight density.
That would be the weight density because you have your 1,000 kilograms of mass per meter cubed times 9.8 gives you force, right? So that's the weight density for metric. For English, 62.5. Okay, so to get the total amount of weight of water, if you were in the English system, it'd be your weight density times your volume, right? Weight density times volume will give you, so pounds per foot cubed times number of feet cubed will give you pounds. And if you were in the metric system, what would the total weight of the water be in the metric system? 9,800 times the volume of the water, right? So if you're in the metric system, it'd be this 9,800 times the volume of water, and that would give you your force. And then your work is going to be, so that force is the weight, and then the work required would be how far you have to lift that. How far you have to lift that weight of the water. Force times distance. Yeah?
What is this symbol here with the scribbled X?
What's the question?
Above water, there's a symbol with like circled X.
Oh, that's nothing. That's just part of the screenshot from my this. Sorry. That's a W, water. Okay, so that's the basic premise. So again, so here's a new context. And remember I told you in the exam, so we're going to look at these different contexts in the homework, and then the exam, you're going to have new context where you're applying all these same principles. So let's practice. Let's see if you can do a problem now without me doing one first. This is practice for the test. So a circular above ground pool has a diameter of 20 feet and a depth of 4 feet. How much work is required to remove all the water from the pool into this hole?
What do you mean by remove? Just like lift it above?
What the least amount of work to get it out the pool, out of the pool. So what will be the minimum amount of work? What's that? Well, how much work is required to move something left and right?
Force times distance.
0. Because it takes no force to move something horizontally, unless there's a resistant force like friction. You're pushing something. So the only force that you have is from lifting it. Right? So when I move this, if I took the bottom of this chain and I lifted it straight up, it'd be the same thing as if I did this.
Really?
Yeah. It takes no work to move something horizontally. There's no resistant force. There's no force to move it horizontally. Weight is an up and down force. So it resists lifting it up. It does not resist left and right.
You can just like maintain height against gravity. No.
But, okay,
Or it's negligible.
no, there's no force. There's no force it's taking to push it horizontally. There's no resistance horizontally. So so yes, you're holding it up, but you're not moving it any distance up and down, so the work is 0. Does that make sense?
I can reframe it.
Okay, so see how you're doing this. See if you can make any progress on this. Okay, so make a group. So get a group of either a partner or a group of 3 and talk through this together. When you're ready.
So I have a bunch of and this is the tank is
Completely full. So the hint is, think about the second way that we did the chain problem.
yeah.
Okay? Think about the second way that we did the chain problem. That's your hint. And let's make, so we're all on the same page.
So we need to figure out how much.
So we're all on the same page. We're going to make x be the distance down from the top, okay?
So the volume is pi 10 squared 400 pi. That's the R. If the diameter is 20. Right. Alright. So check out the 400. Okay. So that's how much water we have. So 400 times cubic feet. So now let's find the weight. So we have 100 times cubic feet of water. And we have cubic feet, 62.5 pounds. 1 cubic foot. 62.5. Multiply that.
So we can get, using a layer, the work on that layer will be the same everywhere, right? Because it's the same distance. Okay, so we want the work to get this layer out. So it'll be force times distance. What's the distance? It's got to go. No, what's the distance this layer has to go to get it out of the pool?
X.
X.
That's
Just X. That's the distance from the top, right? We got to get that layer. Once we get it to the top, we essentially have gotten it out of the pool. All right, now what's the force of that layer? So now we're going to lift that layer, and the force required to lift it is, in general, the force required to lift that layer?
The weight,
The
right?
weight of that layer. The weight of that layer of water. Which is going to be 62.5 times
R squared H.
the volume, right? The volume. 62.5 times the volume, which is pi
Pi 10 squared H.
r squared. And what's h for that layer?
X.
H for the layer?
Delta.
Delta x, right? It's just like a pancake. And we're gonna that's the force. It's the weight density times the volume is our force or our weight times how far we have to move it. Again, was we got to get that up a distance of x, and we're gonna do that from
0 to 4.
0. It's gonna be the first layer at the top, all the way to 4. It's gonna be 0 to 4. 62.5 times pi times 10 squared x dx. Total work.
So really, it's all the setup. Like the integrants are going to be simple.
What's that?
Like the integrants are going to be pretty simple, just collecting the constants, and then like, are we ever going to go higher than degree 1?
Yeah, we're gonna see. Yes, definitely. We see more complicated, but this is an easy one to start. Okay.
Mr. Ashford?
Yes, please.
This Why do you have to include the x in the integral?
Because work is force times distance. And the distance we're moving that layer is x. That's the distance. Force is the weight of that layer of water. And the distance we're moving that layer is x. To get it to the top.
Okay.
To get it out of the pool. So that I just rewrote that. The total work is the sum of little bits of work. The total volume is the sum of little bits of volume. The total area is the sum of little bits of area. Okay, ready to try a harder one for your sheets, but also I would recommend you work it in your notes too. Oh, so did we get the same thing here? Is that what we got?
Yes.
Okay. So here is a little smaller. Not that small. It's good. So we've got a trough. A trough is like what animals drink out of, okay? Long. All right, and so it's got a spout. So let's see. It's triangular in shape, like this. And this says, so it's full. I'm just showing it partially full, but say it's full. We want the work to get all of the water out of that trough, and all the water out of the trough means it comes up out through the spout. Okay, so the water's got to get up out through the spout in order for it to empty out. And so this one is in meters, so we can erase this. Just do a different screenshot. So just notice that the picture is for when we're about halfway done. The problem you're doing is that the trough is full. Okay, it's full to the top. Somewhere in the process, it looks like this, but you're going to calculate the work to empty a full trough out through the spout. We're just set up the interval. Okay, we're just going to set up the interval. See how you do. So work together. Make sure you have this example for your notes, but we're going to put this on the sheet. Okay. Go. And I can help too.
That's at the top.
And we want to have time for one more example, so
Yes.
just try to get done
Yeah.
in 10 or 15 minutes. Let's see how we can do it in 10 or 15 minutes.
19.
One more time. Yours is full. The total work for a full trough, to get all the water out of a full trough, the picture I'm showing would be like when you were halfway done. Okay?
Okay, so
Distance.
so the force is
Well, the distance versus the distance you move out should be out 2 meters. 5 meters. Well, you have to be x plus 2.
we gotta put 5 foot.
I know it's 5 so,
Is that true? 5 foot?
well, yeah, it's
Horizontal.
You know how much there is?
well, you just
What's up?
Water away.
so that's fine. But
Nope, you just have the dimensions of the triangle, all the dimensions.
yeah, but
Distance any
3 meters high this way.
what's going to move? Yeah,
It's 8 meters this way, and it's 3 meters wide that way.
Yes. Yes. No,
Yeah, I think it's
I think so.
x plus 2. Yeah, because x is the height of the
Oh,
Yeah,
so
well, I'm just considering how much each level. Each
Okay, so we're on the same page. Let's make x equals 0 the top of the spout, so we're all on the same page.
Alright, so just move x. Okay, just move x. Remember the last problem? Every this is a quad cube. Yeah, like the so the distance to move. Track is a little cube. Okay.
No, it's just going up.
Yeah, so this vertical distance is x. Yeah. Yeah. Okay. Force.
Now force.
That's the weight of the wall.
So that's going to be 2.5 times it's 1. Yeah, 1. Obviously, yeah, it's on so it's 1,000 kg. 1,000 kilograms. Then multiply by 1.
Is that a rectangle?
What's that?
Is that a rectangle?
You have all the dimensions. It's 3 meters deep, it's 3 meters wide, and 8 meters long. What's that? Shoot. How does it do that? Oh, that's after the.
So 98 here.
Alright, so what'd you say?
So
8 times
W.
So it'd be 8 delta x, and you want to call this W? So our little delta volume is 8 W delta x. We need that in terms of x. How are we going to get that in terms of x? We need a function of x for that.
What is a kilogram meter? Is that sensible?
A kilogram meter, no. A Newton meter is a joule. Remember we talked about.
What is the units of the 9800 conversion?
That's Newton. Check your notes.
Meters?
Check your notes. It's newtons per meter cubed. So we need that as a function of x. So we gotta what? We gotta figure out when x is what? What's W? So when x is 2, W is good, and when x is 5, okay. What's that? So the rate of change is -1. Now we don't have the y-intercept right up, so somehow, some other way, we're gonna have to get it, right? So you could do y minus W. You need some other way of getting that. You don't have the y-intercept right in front of you, right? You don't have 0 something. So you could use like point slope form. And so what is W? W then is -x plus 5. If we're not sure, check, right? So check. When x is 2. Does it work? Yeah. How did I do what? I'm kind of working through this right now, so can I just hold on a second? Do you see it? So what is delta V?
Yeah.
8 times what? Right? And so then what's the weight? Is that, how would you get the weight?
It's like this is a constant. So we take
That's you told me the volume times.
So this is going to go into how much
And 800 newtons per meter cubed. times delta V, we just did. And what's a little bit of work then?
When we have
No, a little bit. We're still doing a little bit of work. We, a little bit of force times the distance that has to go. How far does this thing have to go? What?
Or 5 meters.
3.
No. No, delta x is this. This is delta x.
X.
How far does this layer have to go at a depth of x? Tyler? No, x. So therefore, it's going to be the integral from what to what?
0 to 5.
Try again. So where's the first layer? The first layer is not at 0. First layer is not at 3. Where's the first layer that we're going to take? The top of the tank is x equals what? 2. 2. Last layer is at 5. And now we're going to, what? If we want the total work, we're going to take the integral of what? Quick. If we're going to we want the total work, we're going to take the integral of little bits of work. Little bits of work. If you want the total volume, you're going to take the integral of little bits of volume. If you want the total area, you're going to take the integral of little bits of area. Okay. What's our little bit of work? It's going to be 9,800 times 8 times negative x plus 5 times dx times, so that is what? That's the weight of the layer, right? That's the weight of the layer, and then it needs to go a distance of x. Anybody get it before I put it up? Exactly, just like this.
So the x is not in the.
Of course it is. Of course it is. Multiplication is commutative. I'm just showing it as force times distance.
First, what is a commutative function?
You can change order.
So, the integrand is in newtons. So when we integrate, it takes those meters. We're going up a degree.
No, the integrand is in joules. If you want total work, you integrate little bits of work.
So it's newton meters. So when we integrate
Newton meters is joules.
so it doesn't take to meter.
If you want total work.